Hey everyone, welcome to Professor Long's Lectures in Microbiology. I'm Professor Bob Long. Now these videos are intended for use by students who are enrolled in my Biology 2420 or Microbiology for the Health Science class at Del Mar College. If anyone else out there in YouTube land finds these helpful, by all means please hit like and subscribe. If you're in my class and watching the videos, please hit like and subscribe or provide me some feedback so that I know if they're good or not, which ones are good, which ones need some addressing, so that I can continue to refine these and make them better. Now all of these videos are shot in one take with my cell phone and a board. I don't edit them or don't do anything. These are just what they are. Eventually I'll get into editing them and making them nice and slick and all of that stuff. Now, if you're enrolled in someone else's class, either at Del Mar or somewhere else, they may go into a little bit more different detail or cover things differently. The first few videos that we've done have been chapter 1 of most textbooks, an introduction to microbiology. We talked about some terminology. We learned different types of, we learned a little bit about taxonomy. We learned the different types of microbes that we can look at. What is microbiology? What defines life? We also did a little history of microbiology and the types of microbes that we study and the reasons that we study microbiology. All of that information you need to know, and I tried to pull out the most essential stuff. Now, we're about to do chapter 2. Many instructors gloss over chapter 2 because you are usually required to have chemistry as a prerequisite to microbiology. But I'm wise enough to know from my own personal experience that my first 2 semesters in college, while I was pouring all this information into my brain and could make good grades on exams, I really didn't understand why I needed to know what and what was really important. I was just learning it all. And it was almost what I call information bulimia. You scoop it all in, you make an A on the test by puking it out, and then you walk away and you don't really gain much from it. It's not useful. And I decided to take my approach when I started tutoring and teaching people that what were the important concepts that you need to learn at this stage that you're going to relearn at the next stage and add more detail to. And if I try to teach you everything there is to know about chemistry or in the microbiology textbook right now, you're not going to learn a whole lot because it's not all going to stick. We can only consume so much, digest it, absorb it, then consume a little more, and eventually we build this big picture of what microbiology is. So, I know in one semester of chemistry you may have learned a lot, but I'm going to refresh your mind, and I am going to test over chapter 2 for those of you who are in my class. This is the important stuff that I think you need to know, all right? So let's start talking about some chemistry. And again, this is a basic overview of the major points in chemistry that you should have covered that we're going to utilize in microbiology over and over and over again, and then we'll add some more later on. Now, when we talk about chemistry, the first thing we have to talk about is what is matter. So when we talk about matter, and I'm not going to write all these definitions on the board for every one of these words, but when we talk about matter, what we say matter is anything that occupies space and has mass. Basically, everything in the universe that we think of, unless there's a vacuum present, is matter. The air is matter, our skin, the board, everything that we see and touch is matter. It occupies space and has mass. And even air, we know, we can demonstrate that it occupies space and has mass, because if you blow a certain type of air into a balloon, not only does the balloon stretch, but the mass of the balloon may cause it to be greater than the mass of the molecules surrounding it, and the balloon will sink to the ground. If the mass of the balloon is less, then it will be supported and sometimes can float off. Now, all matter exists in 4 different states. There's 4 states of matter. When I was a kid, we learned 3, but now a 4th one has been discovered by scientists or manufactured, or however you want to see it. Okay? Matter exists in solids. That would be things like the board or a desktop or a rock. It's solids. There's liquids, the ocean, water, coffee, a soda, whatever you're drinking, any liquid. A gas, the air that is around us, the air we breathe in and out, the steam coming out of a pot. And plasma. Now plasma is somewhere between a solid and a liquid. And it's kind of pliable like a liquid, but it doesn't lack viscosity and is very runny. I think of plasma as kind of like the stuff that's inside of a lava lamp. It's not quite solid, but it's not quite liquid either. It's I don't know, amorphous. Anyway, those are the 4 states of matter. You should know them. Now, when we talk about chemistry, one of the more important things that we talk about are the elements. And one of the definitions of an element and you should know this definition, is an element is all of the atoms that contain the same number of protons. Well, that doesn't mean anything to us yet if we don't know what protons are. Let me make sure I'm within range of view. I didn't right off the edge of the board. Yeah, I did just a little bit. So let me move my camera just a hair. An element is all of the atoms that consist of the same number of protons. Okay? Now, what does that really mean? Well, we're going to get into the structure of an atom in just a moment. So, when I have an atom, all atoms are comprised of some combination of subatomic particles. An atom is nothing more than a collection of subatomic particles that come together and exhibit a unique and identifiable behavior. So each subatomic particle that we're going to talk about has its own behavior, and they behave independently of each other, but when they come together as a little team and they start to behave in a way where they accomplish, one way I think of it as a common goal, but what we call a unique and predictable behavior, we call that an atom. An atom is nothing more than a bunch of subatomic particles working together, so to speak. There are 3 subatomic particles that we're going to talk about. One is called a proton, and you should know the abbreviation of a proton. It's a P with a little positive like a superscript up there. So anytime you see this, or when we're drawing atoms and we see a positive charge, we're talking about protons. And there's another one called a neutron. A neutron is abbreviated as an N with a little ought or 0 as the superscript, which indicates that it does not have a positive charge. It's also lacking a negative charge, which is what they called an electron. And electrons are abbreviated as an E with a little negative superscript. Okay? These are the 3 subatomic particles. And all atoms are some combination of these subatomic particles. Now, all atoms that we're going to talk about are some combination of protons, neutrons, and electrons, with the exception of one atom. When we talk about hydrogen, it's only a proton and an electron. It lacks any neutrons, and we'll talk about that in a little bit more detail. So in order to build an atom, all I need is some protons, some neutrons, and electrons, and I need to put them together in a specific arrangement. Now, protons have a different behavior than neutrons and electrons. And that behavior, all protons that exist as individual units in the universe will behave in a specific way, and that behavior they indicate with a positive charge. It's kind of an arbitrary name given to it. All neutrons behave like all other neutrons, and all electrons behave like all other electrons, and they all 3 have different behaviors from each other, or perform or do different things individually. Now, if I wanted to build an atom, what I could do is I could take some combination of protons, neutrons, and electrons, and I would have a certain atom. And if I have another atom, or a whole bunch of atoms that all have the exact same number of protons, we call that collection of atoms an element. Okay? Now, what do we mean by all this? So, one of the best ways for me to try to get this across to you is to try to build an atom for you and draw one out. Now, excuse me a second. You guys have to forgive me. I do all these in one take, and sometimes my voice gets a little roughed up after talking so much. Now, what makes one atom different from another atom is the arrangement of the protons, neutrons, and electrons. And each atom, based on how it's assembled, if I have 2 atoms that are identical, that means they have the same protons, same neutrons, and the same electrons in the same arrangement, and they're both going to exhibit the same identifiable or predictable behavior. So those 2 atoms are the same. Another atom, if it has a different number of protons or neutrons or electrons, may behave differently than these other 2. And that's what makes one atom different, is how do we arrange the protons, neutrons, and electrons. Now, chemistry is the study of the interactions of atoms and molecules based on those arrangements of protons, neutrons, and electrons. So when we talk about chemistry, we're talking about the study of the behavior of atoms, and we'll leave it at that. Now, one of the things that you need to know is this. When we talk about an atom, we're going to talk about the atomic number. The atomic number indicates the number of protons in the nucleus of an atom. So atoms have a nucleus. They have a little central region that's densely packed with protons. It's also where the neutrons are found in an atom. And in many instances, the number of neutrons can be equal to the number of protons, but we're not going to get into that just yet. Well, another thing that we know about atoms is that atoms are electrically neutral. So to be electrically neutral, since I take an atom, if I have an atom that I know the atomic number, which tells me how many protons there are, and protons have a positive charge, and that atom is electrically neutral, then the atom must have the same number of electrons. So one good example I want to draw out for you is, for example, let's look at a hydrogen atom. The chemical symbol for hydrogen is H. Hydrogen has the chemical number, or the atomic number 1. That means it has 1 proton in its nucleus. And around the nucleus of an atom is where all the electrons are whizzing around. Now, it's really hard to get this concept across to people. It's really hard to wrap our brain around it because it's an intangible concept. It's what we call an abstract concept. You can't see and touch it, but you know, we live in South Texas here, and we have high humidity. We're by the ocean, and we're surrounded with the bayfront and a beautiful ocean, beautiful beaches, and so it's very humid in this area. And that humidity is just moisture, little water molecules that are moving around in between the other gases in the atmosphere, independent of each other. And when I'm talking about this, when I talk about a proton, a neutron, or an electron, a proton, neutron, or electron is a little condensation of energy, okay? And so there's other subatomic particles we can talk about, things like quarks and other things. And they're little bundles of energy whizzing around the universe, and when 2 of them come together and start interacting, they can form these subatomic particles. And when these subatomic particles that have opposite charges, like protons and electrons, come near each other, they can start interacting in a way that they hang out together, so to speak. And all they are is condensations of energy. But we can't see and touch and feel that concept. So I like to use humidity as my example. I can't see and touch the humidity in the atmosphere. I can't. But when I wake up in the morning sometimes, I see moisture on the windshield or dew on a leaf. And that's because some of the water molecules out in the atmosphere came close enough together to form these hydrogen bonds and start interacting with each other. And then more water, and when the water becomes so dense that it cannot be supported by the other air molecules, it precipitates out of the atmosphere as a droplet. Well, that's kind of how subatomic particles are. These other structures, called quarks and other things, come together and they form protons, neutrons, and electrons. And then as the protons and neutrons and electrons come together, they form atoms. And they're just little condensations of energy that's, bubbling around. Well, it turns out that the protons can all be compacted together with neutrons in the nucleus, but the electrons are whizzing around with their energy in a little area outside the nucleus. To me, it almost looks like, when you think about what an atom should look like, we tend to think of our solar system, with the sun being a nucleus, and then the planets moving around as electrons. It's not exactly like that because the electrons don't just stay in an orbit, even though we call it an orbital. It's really more of a cloud where the electron can whiz around anywhere in this little space. And because there's a certain amount of energy to electrons, they can only occupy so much space or have so many crowded together. But essentially what happens is, I can have my nucleus with a proton in it, and then I would have my little electron whizzing around outside of this, in an area where it's predictable to find. Based on their opposite charges, they're somewhat attracted to each other. So the electron is being held near this proton, whizzing around it in 3 dimensions, based on their electrical attraction. This is an atom of hydrogen. 1 proton, 1 electron. Now, if I were going to do an atom of sodium, excuse me for a second, anyway, so if I were to look at an atom of sodium, sodium has the atomic number 11. That means it has 11 protons. That means it has to have 11 electrons. Now there's a thing in at least the chemistry of some of the lower atoms, the ones that have small atomic numbers, like the first 16 to 20 or so, that we call the 288 rule. And the 288 rule basically tells us how many electrons can fit in this electron cloud. The first electron cloud or orbital can only hold 2 electrons. The second electron, if I try to stick 2 electrons in an orbital that can only hold 2, if I try to stick a third one, it will pop out into a new orbital and it will whiz around in another one. Okay? For example, well, I don't want to do another atom, let's just stick with sodium. Once I fill the second orbital, any additional electrons have to go into the next orbital or the next electron cloud. So since I have 11 protons in sodium, I'm going to have 11 electrons if it's neutral. And it turns out that the first orbital can hold 2 electrons. If I try to shove a third electron in there, it's going to pop out based on the number of electrons in this small space. So I can therefore start adding up to 8 electrons, and all this has been figured out by physicists and chemists, and we're not going to have time to go into all the whys. You'd have to take a couple of years of chemistry with a lot of physics to understand it all. But now I have 10 electrons and 11 protons. I need 1 more electron. I can't fit it in this orbital, so I'll stick it in the outermost orbital here. And this is what an atom of sodium would look like if we did what we call an electron diagram of an atom. This is an electron diagram of hydrogen, a single proton with a single electron. This is an electron diagram of sodium. Although sodium will have some neutrons in here, we're not going to worry about the number of neutrons, okay? That can vary, and the atomic weight is going to tell you the number of neutrons based on how many protons there are. We're not going to get into that level of chemistry right now. I just want you to understand what is the structure of an atom. Atoms are electrically neutral, and the atomic number tells us how many protons there are. If it's electrically neutral, then I know how many electrons there are. If I understand the 288 rule, for at least the first 18 atoms, from 1 through 18, I can figure out what the electron diagram would look like. Beyond that, it gets a little bit different on how the orbitals are formed and shaped and all of this, and we're not going to get into that chemistry. Okay? So this is kind of a simple idea, all right? Now, there is a concept called an isotope. So let me do this, okay? I'm going to erase these 2 atoms. I'm going to erase all this information. And we're going to talk about what an isotope means. Anytime we see iso in biology or chemistry, it means same. And tope refers to topography or layout. So the same layout, when we have an isotope, isotopes are atoms with the same atomic number but different number of protons. Different number of neutrons. So when I look at an isotope, I can have 2 atoms that have the same atomic number. They would have the same number of protons and electrons, but between the 2 different isotopes can have 2 different numbers of neutrons. So, for example, carbon has the atomic number 6, right? So carbon is going to have 6 protons in its nucleus. it's going to have 6 electrons whizzing around the nucleus. We can only fit 2 in the first orbital, and then we're going to have 4 whizzing around in the second orbital. And that's it. Well, one form of carbon can have 6 neutrons, and if I have 6 neutrons, then we call this carbon 12. There's another form of carbon that would have the exact same layout. And we would have 6 protons, but if I have 8 neutrons in the nucleus, I'm still only going to have 6 electrons whizzing around it. The atomic number tells me how many protons, therefore I have the same number of electrons if it's an atom because it's electrically neutral. But these two different forms of carbon, one has 6 protons, we call that carbon 12, and this has 8 neutrons, we call this carbon 14. They are isotopes. They have the same layout, they just have a differing number of neutrons. So anytime we talk about an isotope, that's all that we're talking about. There's 2 atoms with the same atomic number, the same layout, but differing number of neutrons, okay? And sometimes you'll hear people talking about carbon 12 or carbon 14 when they do what's called carbon dating, and we look at the decay rate of the 2 and blah, blah, blah. We are not going to get into that stuff, okay? So now, we know what an atom is. We know what the 3 subatomic particles that make up an atom are. We know that the nucleus of an atom contains protons and neutrons very tightly packed, moving around each other. And the electrons are whizzing around very loosely out in these things called electron clouds or electron orbitals or electron shells. And by the way, the outermost the outermost electron shell or electron orbital is called the valence orbital. You'll see this term, and it's going to be important to us. The valence orbital is the outermost orbital of electrons on an atom. You need to know that because we're going to look at the valence orbital, and it's going to allow us to predict the behavior of certain atoms and if those atoms would ionize. Okay, so we're going to talk about what an ion is. All right. So before I get into that, you guys need to know what is matter, what are the 4 states of matter, what are atoms and elements, what are the 3 subatomic particles. You need to know that the atomic number tells us the number of protons. Because atoms are electrically neutral, they have the same number of electrons, and an isotope is 2 atoms of the same atomic number, same number of protons, but differing number of neutrons. Okay? Now, we're going to talk about an ion. And the easy way to think of an ion, in my opinion, is an electrically charged atom, which means it's not really an atom any longer. But it's an atom that has gained an electrical charge. Since the protons and the electrons are what are carrying the charges, and the protons are densely packed in the nucleus and hard to get to unless we do a lot of nuclear chemistry and nuclear physics, it's the electrons that are really going to determine a lot of the behavior of the atom, so to speak. And as the number and the arrangement of those electrons, as they're whizzing around in those electron clouds, that allow us to predict the behavior of most of the atoms or elements. So, if an ion is an electrically charged atom, how do atoms gain charges? They can either take on electrons or give off electrons. And one way to determine if it's going to ionize or not is to look at the outermost orbital for some of the atoms. And we're going to talk about the difference between an ionic bond and a covalent bond, and how we predict which one will happen is a little fuzzy, but just bear with me for a second. Okay? Now, if I were to draw sodium again, so we said sodium has the atomic number 11, so it's going to have 11 protons in its nucleus. And it's going to have 11 electrons. There's 2 electrons according to the 288 rule in the first orbital. There's going to be 8 electrons in the second orbital, because that's the most that it can hold based on some physics. And there's going to be a single electron to give me 11 electrons in the third orbital. This outermost orbital, called the valence orbital, has only one electron. Now, I hate to give human traits to non-human things, but an atom is not really balanced energetically, so to speak. Electrically it's balanced, but its energy, it needs to have the outermost electron filled with as many, the outermost orbital filled with as many electrons as it can possibly hold. And I only have one electron in the outermost orbital, but it turns out that the outermost orbital, at least for electrons of this size, atoms of this size, can only hold up to 8 electrons. Well, I have two choices here. I can take 7 other electrons that are whizzing around in the universe, and if they whiz close enough by, they can get pulled into the orbital. Or I can just release this one and make this the valence orbital. And the question is it easier to gain 7 electrons or lose 1 electron? And if I asked you to grab some heavy textbooks, and I have 2 tables, 7 on one side and 1 over here, and I told you I need a pile of 8, I don't care if you move 1 book to this 7 or these 7 to that 1, I just need all 8 in a single pile. You're probably going to move the individual textbook to the other pile because it's more energy efficient. And if Mother Nature is nothing, she is efficient when it comes to energy. And so rather than trying to gain 7 electrons here, Mother Nature will kick this electron off into the universe, whizzing around the universe without an atom attach to. And now I have an ion. Now I have the sodium ion. And the chemical symbol for the sodium atom is Na. When a chemist sees and natrium is the Latin name for sodium, that's where the Na comes from. When a chemist sees Na, they know, well, okay, there's got the same number of protons and electrons. When they see Na with a little superscript positive charge, what that means to them is, oh, that's the sodium ion. The sodium atom, the sodium ion, same number of protons and electrons. This one has lost an electron. It has subtracted a negative and become positively charged. And essentially, if I look at it, it has 11 protons, but only 10 electrons. And if I do that math, I have 1 extra positive charge. And so this is why we draw the ion of atom with a positive charge. Okay? Now I can look at another atom, and we're going to. Let's do the chlorine atom. When I look at chlorine, it has the atomic number 17. So it's going to have 17 protons in its nucleus. We're not going to worry about the number of neutrons right now. That means it's going to have 17 electrons in its orbitals. The first orbital can only hold up to 2. The second orbital can hold up to 8. I was counting 1, 2, 3, 4, 5, 6, 7, 8. That's going to give me 10. I need 7 more. 1, 2, 3, 4, 5, 6, 7. So the chlorine atom has 17 protons and 17 electrons. If we drew its electron diagram, this is what it would look like. Is the valence orbital, the outermost orbital, completely filled? And the answer is no. It could either lose 7 electrons or pick up 1 that's buzzing around the universe independent of its atom. And so sometimes what happens is one atom will give its electron to the other. The valence electron from sodium sometimes can be given to chloride, and now chloride has 17 protons, but it has 18 electrons. So when I draw the chloride ion, it has a negative charge. This, to a chemist, means it's got the same number of protons and electrons. This means it has 1 more extra electron or an extra negative charge. Well, some atoms can ionize, and we can look at the valence orbital and we can predict if it will ionize. And usually, for reasons we're not going to discuss, if there's only 1 electron or maybe 2 electrons in the outermost orbital, it'll give those 2 electrons off and gain a positive or 2 positive charges. For example, you'll see calcium sometimes written this way. When I write the calcium atom, it's Ca. If I write the calcium ion, it can either be written as Ca2 plus or Ca plus plus. And what that indicates to a chemist or anyone who understands it is it's lost 2 electrons, it has 2 extra protons. So it's ionized. So that's all that an ion is. An ion is an electrically charged atom, and the atom can become charged by gaining negative charges, electrons, or losing negative charges, electrons, and becoming negatively or positively charged. This is a positively charged ion. We call that a cation. It's the word cat and ion. That's a positively charged ion. If it has a negative charge, it's called an anion. It's a negative charge ion. And cations and anions can interact with each other because this one has a positive charge, this one has a negative charge, and oppositely charged substances will attract each other. They can form a bond between these 2 ions called an ionic bond. And in that ionic bond, anytime we talk about what's called an ionic bond, this is a bond formed between atoms that have ionized. Electrons are transferred from one to the other. Okay? And my penmanship near the board is terrible, but electrons get transferred from one atom to another atom, and when they ionize, become oppositely charged, then they can form a chemical bond. We call those ionic bonds. Bonds formed between atoms that have ionized, or it's a bond formed between 2 atoms that have transferred electrons from one to the other. Let me make sure everything's within the view of my board because I lined up my camera and sometimes it's hard to see. Yeah. So, now, there are other types of chemical bonds. In order to understand this stuff, you need to know that atoms are made up of some combination of protons, neutrons, and or electrons. All atoms are combined of a combination of 3, except for hydrogen. It's only 1 proton, 1 electron. If we draw an electron diagram, we have to use the 288 rule for the simple atoms, and we can figure out using the atomic number what the atom would look like. Then we can look at the valence orbital and determine if the atom would ionize. If it only has 1 or 2 electrons in the valence orbital, it's going to lose those. It's easier to lose 1 than it is to gain 7. It's easier to lose 2 than it is to gain 6. Now, if I have 6 or 7 electrons in the outermost orbital, the valence orbital, it's easier to gain 1 or 2 electrons, and some atoms will do that. Okay? Now, I think you need to know what a cation is. You certainly need to know what an anion is. Cations are all positively charged ions. Anions are all negatively charged ions. Okay. All right. So I'm going to erase this, and we're going to start talking about what's called a covalent bond. Because not all atoms ionize, even if they can. For example, if I have 10 hydrogen atoms, I may not get 100% of those, or all 10 of them, to ionize. A couple might ionize, the others may not. So, just because an atom can ionize doesn't mean it ionizes all the time. They usually do when mixed with other solutions or other substances, but not always. And so, we don't always get 100% ionization of a particular atom. Now, knowing that, some atoms, when we look at their electron diagram, it's not easy for them to ionize. A really good example is carbon. If I look at carbon, it has the chemical symbol C. Carbon has the atomic number 6, so we know it has 6 protons in its nucleus. And I told you before it could have 6 or 8 neutrons depending on carbon 12 or carbon 14. We're not going to look at the neutrons. So I know I have 6 electrons for a carbon atom. 2 in the first orbital, and it turns out that I have 4 out in the valence orbital. Well, is it easier to gain 2 electrons? Is it easier to gain 4 electrons or lose 4 electrons? And I'm going to use this color blue, this marker, because I think the other marker is not showing up very well. Well, it's about 50-50. So it turns out that carbon does not ionize, or it doesn't ionize very easily under normal circumstances. We can force it to. So now, I'm going to draw a little lowly hydrogen atom. My hydrogen atom has a single proton and a single electron. And if a hydrogen atom comes close enough to a carbon atom, it turns out that these protons here have a slightly greater pull on this electron than this single proton. And what will happen is this electron can be shared between this hydrogen and this carbon. And what happens is this electron will spend some time around this and some time around this, and it will whiz around both nuclei, sometimes satisfying this electron pair here and satisfying an electron pair here. And the physics of it is beyond our explanation for now. Well, if that can happen, and I have another hydrogen atom here with its electron, then they can form a little bond where these 2 electrons are shared. They spend an equal amount of time around each nucleus doing this. And I can do this up to 4 times. I forgot to put the electron orbital here. If I do this up to 4 times, now I kind of satisfy that sometimes this outer valence orbital has 8 electrons, and sometimes this valence orbital has 2 electrons. And these bonds are sharing electrons between the 2 valence orbitals, and so we call this a covalent bond. Okay, covalent bond is formed when 2 or more atoms, but we'll say 2 atoms, share electrons. Ionic bonds form when 2 atoms transfer electrons from one to the other. A covalent bond is where 2 atoms share the electrons. Sometimes the electrons are around this one, sometimes they're around this one, and when I do all of this, they kind of both get balanced out. And this would be an atom of what we call methane gas. Methane gas is abbreviated as CH4. And it turns out that the carbon atom can always form up to 4 bonds with other substances. And so, now I'm not going to get any more complex than that for now. All right? So you need to know the difference between an ionic bond and a covalent bond, and particularly when we combine carbon with hydrogen, we can get a bunch of covalent bonds as they share their electrons. And by the way, this leads us to the difference between what we call organic chemistry and inorganic chemistry. When I talk about organic chemistry, so I'm going to erase this now. But when I talk about organic chemistry and organic compounds or organic molecules, by the way, a molecule is formed when 2 or more atoms come together and form a bond. We call those molecules. And it can be an ionic bond, it can be a covalent bond, they can even be 2 atoms of the same name and atomic number. For example, 2 hydrogen atoms can form a bond between each other, a covalent bond. That's how we get hydrogen gas, H2. I have a hydrogen atom here and a hydrogen atom here, and their valence orbitals can share those electrons, and they can form a covalent bond so that electrons are whizzing around as a pair around both of them, and they form a covalent bond. Okay, so they can be the same atom or they can be different atoms when we form bonds. Okay. Now, I hope that didn't provide any confusion for you. You need to know the electron diagram of an atom. If I give you an atom and its atomic number, could you draw an electron diagram using the 288 rule? And then can you look at the valence orbital and predict if it will ionize or not? Usually, a general rule of thumb, there are exceptions to the rule, is that if it needs 1 or 2 electrons in the outermost orbital, it will ionize and gain 2 electrons. If it has only 1 or 2 electrons in the outermost orbital, it will ionize by losing that 1 or 2 electrons. Okay? If 2 different oppositely charged atoms form a bond where they transfer electrons from one to the other, we call that an ionic bond, like sodium and chloride. Okay? Or potassium and chloride could do the same thing if we did the electron diagram of potassium. Draw out potassium, look up its atomic number, draw out the electron diagram, put it next to an atom of chlorine, and draw the chlorine atom with its electron diagram, and predict if they will ionize and form an ionic bond. Now, covalent bonds are formed when 2 or more atoms share electrons from their valence orbitals. And that's about, well, there's one more type of bond called a hydrogen bond, and we're going to talk about it. In order for us to talk about hydrogen bonds, we need to talk a little bit about water, okay? So let me take a quick drink. Make sure I'm going in the order of my notes. So we've talked about chemical bonds, we've talked about ionic bonds and covalent bonds. We're going to talk about hydrogen bonds in a second, but in order to do that, I think it's really important to talk about hydrogen bonds. And actually, we really need to talk, before I move to hydrogen bonds, I should probably talk about polar covalent and non-polar covalent bonds. Okay? So when I look at carbon, or when I look at methane gas, CH4, if I were to look at the electron diagrams, here, let me move this over a little bit so I have some room to write this way. If I look at methane gas, my carbon is going to have all of its protons and electrons, but it's going to have 4 hydrogen atoms bound to it. And anytime we see one of these lines forming a chemical bond, that line essentially means there's 2 electrons being shared between those 2 atoms. So I would have 2 electrons here from the valence orbitals, 2 electrons here, but they don't like to draw those little electrons in. They just put a straight line, and that means it's a covalent bond. Okay? Ionic bonds usually don't have a line, so we would draw sodium chloride like that. And what that means is this guy gave one of his electrons to this guy. He's got a positive charge and he's got a negative charge. Now, that's an ionic bond. This is a covalent bond. This happens to be what we call a non-polar covalent bond. What in the world does that mean? Non-polar means I have equal sharing of the electrons between the 2 atoms. What that means is these 2 electrons spend an equal amount of time here and here, so that there's no polarity, there's no electrical charge gained by either one of them. When I look at what's called a polar covalent bond, what that means is there's an unequal sharing of electrons. A good example is water. So if I look at the atomic number for oxygen, or if I just look at the oxygen atom, oxygen has the atomic number 8, so it has 8 protons. It's going to have 2 electrons in the first orbital. It's going to have 6 electrons in the valence orbital. And the electrons sometimes like to pair up, but based on some physics, sometimes they don't. And I know this because I've studied it and done the behavior of this stuff, but I'm not going to go into why. So now look, if I look at a hydrogen atom and it comes close to this, I got my proton, I have a single electron in the valence orbital. These 2 guys can share these 2 electrons and form a chemical bond here. And I form a covalent bond by sharing the electrons. And I can do that with another hydrogen atom over here with its electron, and I can form 2 covalent bonds here. And now I can have sometimes a total of 8 electrons out here, completely filling all the electron orbitals slots, so to speak. And I have sometimes 2 electrons here, and here, making the valence orbitals filled. Now, it turns out that we don't always equally share the electrons. This big honking nucleus right here, right? This thing right here has so many protons that it's going to pull the electrons over this way a little more often. And they'll spend a little bit more time around the oxygen atom, and a little less time around the hydrogen atom. So there's not an equal sharing of electrons. We call that a nonpolar covalent bond. It's a covalent bond that has unequal, or it's a bond formed between two atoms where there's an unequal sharing of electrons. They share the electrons, but they are not shared equally. And the electrons will spend a little bit more time around the oxygen than they will the hydrogens. So when I draw methane gas, I don't draw any polarity to it. But if I were to draw a water molecule, sometimes we draw water like this. A hydrogen and a hydrogen. But we have a little bit of positivity here. Oops. My bad. There's a little bit more of a positive charge and a little bit more of a negative charge because the electrons are spending more time over here. This is slightly more negative than the two hydrogen atoms. So a polar covalent bond has equal sharing of electrons. A nonpolar covalent bond has unequal sharing of electrons based on the pull of the nucleus of the atom. And that's about all I'm going to say about it for now. Now watch. If I start looking at molecules that have polar covalent bonds, particularly water, and another one that can do it is nitrogen when it forms ammonia. We're not going to do that, but nonetheless, if I have another water molecule here with its two hydrogen atoms, it's got a slightly negative charge and slightly positive charges. If I draw a dotted line there, and it's probably hard for you to see those dots, but a little dotted line represents what we call a hydrogen bond. It's a weak bond based on sort of a negative attraction, but it's not truly an ionic bond yet. I can have another water molecule over here with its slight charges and get another hydrogen bond, and I can have another one like this, and I'll get more of these bonds, and I can start having water molecules with their negative charge forming all of these, what we call hydrogen bonds, because of the polarity of the molecule. Now the nice thing about these is that they can break, and this guy can move over here, and then move around, and they can all break and reorient. But because of these slight positive and slight negative charges, there is an attraction here. It's not quite as strong as an ionic bond, because electrons are not transferred like they are an ionic bond. These guys are keeping their electrons to this water molecule, but because the electrons spend more time around the oxygen, it gains a slight negative charge, and less time around the hydrogen, it gains a slight positive charge, and this creates a very weak bond. We call those hydrogen bonds. Okay? So, essentially, hydrogen bonds, if we want to think about them, is they are bonds formed between polar molecules that have opposite charges. That's about the best way we can define it, and you really got to see it to understand it. So I'm going to erase all those little hydrogen bonds, the dots that were forming the hydrogen bonds, but now you can see how water molecules can interact but still remain fluid. They're bound to each other, there's some cohesion, but they're moving around each other much more easily than ions or than covalent bonds, covalent molecules. So molecules or atoms that form polar covalent bonds can also form usually hydrogen bonds. Now, one final detail. If I were to drop sodium chloride or any ionic molecule in a bucket of water, these negative charges will sometimes want to interact with this sodium. And this molecule can be forced apart or dissociate So that what happens when I combine these two sometimes is I'll get a sodium ion, and it'll be surrounded with the slightly negative parts of water molecules through this slight interaction, and then these hydrogen bonds can sometimes hold the chloride molecule away. And now I have dissolved my sodium chloride in a solution, which is why table salt and other molecules that have some polarity can be broken up very easily when placed in a water solution. And that causes what we call dissociation of the ion, because the negative parts of the polar covalent bonds and the negative part of a water molecule will interact with the positive ion, and the slightly positive charged part of a water molecule will interact with the negative ion. The negative oxygens and the positive hydrogens will move these ionic bonds or break these ionic bonds and cause it to dissolve. That's sort of a neat thing to think about, but I'm not going to test you on that if you're in my class, okay? So, the information I want you to walk away knowing so far is this. I want you to know what elements are. I want you to know the definition of an atom. I want you to know the 4 states of matter, what that definition of matter is. I need you to know what subatomic particles make up atoms. I need you to know the charges of those 3 subatomic particles. I need you to be able to draw the electron diagram of certain atoms, at least the first 18 or so. If I give you the atomic number, could you draw it? And then you could predict whether it would ionize or not. By the way, any atom that has a complete complement of electrons in the valence orbital, where the valence orbital is completely filled with all the electrons it can hold, does not ionize or interact very easily. We call them inert gases. So things like helium and neon, and if you drew them out, if you look up helium or neon and you drew their electron diagram, you would see what I'm talking about. It's probably a pretty good exercise. So you guys need to know what 3 subatomic particles can make up atoms. You need to be able to draw an electron diagram of certain atoms. You need to know that the atomic number tells us the number of protons. Since an atom is electrically neutral, it has the same number of electrons. If you look at the valence orbital, the outermost orbital, will the atom ionize or not? Will it gain or lose electrons? Will it become positively or negatively charged? Will it become a cation or an anion? And then you need to look at covalent bonds and hydrogen bonds. And what is the difference between polar covalent and non-polar covalent bonds? We're going to stop this video for there. There's still plenty of chemistry to do, but we're going to do a second chemistry video. So listen, I hope you learned something. I hope you had as much fun as I did. I feel like this is a little bit choppy. Doing these videos is kind of difficult because it's breaking up my normal lecture style. I'm used to interacting with students, but nonetheless, I'm doing the best I can to deliver this information the best way I know how. Thanks for watching. See you in the next video.